So, welcome to lecture series. In my last lecture, we have discussed about the correlation between any finite dimensional inner product space and a linear functional on that space. We have seen for a given linear functional on the finite dimensional inner product space, there exists a unit vector in the space and your linear functional is expressed as inner product with the fixed vector. Then we raise the question whether this finite dimensional inner product space is replaced by infinite dimensional inner product space, then is it true that any linear functional on that inner product space will be in the form of some inner product with some fixed vector in the space? I told you that answer is no. I mean to say it is not true always. So, to support my answer, let me consider one example. Let V be the all polynomial functions over the field of complex number, and let this be inner product defined by inner product of any two elements f and g in V equal to integration from 0 to 1 f of t and g of t bar dt. So, I am defining inner product like this. Consider Z belongs to the space of complex number, I mean field, complex number. This is a fixed complex number I will consider. Define a function capital L from V to capital F defined by your L of f equal to f of z. So, I am defining a linear functional on this space V as a L of f equal to f of z, for z is a basically fixed point in the complex number, there is some constant quantity. So, certainly we have already seen L define a linear functionals. So, L is a linear functionals, already we have seen. Now, our claim is that for these linear functionals there exists no non-zero element g belongs to capital B such that inner product of f and g will be equal to L of f. Claim for this L there exists no 0 not equal to g belongs to V such that L of f equal to f of z equal to inner product of f and g, that is equal to 0 to 1 f of t and g t dt please. If such g exists, then for h equal to x minus z we have h f of z equal to 0, since h of x equal to x minus z I have considered. So, then h of f of x at x equal to z will be certainly equal to 0. So, this implies I will have L of HF, L of HF which is equal to HF of z is equal to 0 equal to inner product of HF g. If at all there is a non-zero g such that L of f equal to inner product of f and g. So, this is true for all f. So, if I replace f by HF, then also it is true. So, this implies that 0 equal to 0 to 1 h of x and f of x and g bar of x dx. I will have like this, because HF of x equal to h of x into f of x, please. So, this implies this is for all f belongs to capital V. So, this implies for f equal to h bar and g, then also we have 0 equal to 0 to 1 h x, h bar x, g of x, g bar x dx. So, this implies 0 equal to 0 to 1 mod of this h x whole square and mod of g x whole square dx. See, mod of h x and mod of g x are positive function, please, and since g is a non-zero functions. So, this implies that your mod of h x and mod of g x equal to 0. So, this implies, okay, so for this is true for all x belongs to 0 to 1. So, this implies that g x mod of g x equal to 0, because mod of h x is not equal to 0 for all x belongs to 0 to 1, because h at x equal to z only it is equal to 0, please. So, therefore, this is not equal to 0. So, only possibility is g x equal to 0. So, this implies g equal to 0, which contradict our hypothesis that g not equal to 0. So, this implies that does not exist g belongs to V such that inner product of your f and g will be equal to L of f, which is equal to f of z. So, this example basically shows that if we replace the finite dimensional inner product space by infinite dimensional inner product space, then the results, that is for each linear functionals over inner product space, there will be a fixed vector over the space, so that the linear functional can be expressed as the inner product of alpha and beta, that fixed vector. So, here it is not true if it is replaced by infinite dimensional space. Okay, so, we have seen that over a finite dimensional vector space equated with an inner product, any linear functionals defined on the finite dimensional inner product space can be written as a inner product of a fixed vector. Now, let me use this concept to show the existence of adjoint operator. over a finite dimensional inner product space. So, this let me talk in terms of one small theorems. Let V be a finite dimensional inner product space over the field is capital F. Let T be a linear operator on V. Then there exists an adjoint operator T star of T such that inner product of T alpha beta equal to inner product of alpha T star beta for all alpha beta belongs to V. So, here I am going to show you that if a space is finite dimensional inner product space and T is a linear operator defined on it, then there exists a linear operator T star which is called as adjoint of T such that for any two vector alpha and beta, inner product of T alpha and beta equal to inner product of alpha T star beta. So, to prove these results, what I will consider beta be any element of V. Define a function phi from V to F as phi of alpha equal to inner product of T alpha and beta. So, I define a function phi from V to F as phi of alpha equal to inner product of T alpha beta for all alpha belongs to V. So, according to this definition, I can see for any alpha beta belongs to V and C belongs to capital F, phi of C alpha plus beta. So, let me take gamma so not to confuse you, equal to inner product of T of C alpha plus gamma and beta. So, according to the definition of inner product, we have phi of C alpha plus gamma equal to inner product of C T alpha and beta plus T gamma and beta. So, this is equal to C times phi of alpha plus phi of gamma. So, this implies phi is a linear functional. So, phi is a linear functional. So, since we have considered the inner product space is finite dimensional, so according to our last results, so there exists beta prime belongs to V such that your phi of alpha equal to inner product of alpha and beta prime. Phi of alpha I will look like this thing. So, this implies inner product of T alpha and beta equal to inner product of alpha and beta prime. Now, consider a function T star from V to V defined by which is mapping beta to beta prime. See, we have considered here beta prime as a unique vector, because we have already seen for any linear functional, for given each linear functional, there exists a unique element in V such that linear functional has inner product of that unique vectors. So, this beta prime is unique. Now, if I consider a function T star from V to V defined by which is mapping beta to beta prime, then T star is a linear operator. How? For gamma and beta belongs to V and C belongs to capital F, I have to show that T star of C gamma plus beta equal to C times T star of gamma plus T star of beta. Then only I can say T star is a linear operator on B. According to definition, we have inner product of alpha and beta prime, which is equal to inner product of alpha and T star beta. So, this implies inner product of alpha and T star T of beta equal to, that is T star of beta equal to beta prime. Okay. So, accordingly we have, now this is equal to alpha, inner product of alpha T star and C gamma plus beta. We know this is equal to T of alpha C gamma plus beta. This is equal to C bar T alpha and gamma plus inner product of T alpha and beta. This is equal to C bar. Now, T alpha gamma equal to, according to definition, this is equal to alpha T star gamma plus this is equal to alpha T star beta. So, this is equal to inner product of alpha T star and C times T star gamma plus alpha T star beta. So, this implies T star of C gamma plus beta equal to C times T star of gamma plus T star of beta. So, T star is a linear operator on B. Uniqueness of beta prime implies uniqueness of T star. Okay, so, we have seen that over the finite dimensional inner product space, if a linear operator T is defined, one can have another operator T star defined on the vector space V such that inner product of T alpha beta equal to inner product of alpha T star beta. Here T star is called as adjoint of T. So, we have seen existence of adjoint operator of a linear operator defined over a finite dimensional inner product space. Now, let us see what will be the matrix representations of linear operator T and T star with respect to some orthogonal order basis on the space. Let V be finite dimensional inner product space, this is an inner product space. Let alpha 1, alpha 2, alpha n be an orthogonal order basis for V. Let T be a linear operator on V. Let the matrix representation of T with respect to order basis B equal to capital A. Then the entry AJK of the matrix A is nothing, it is basically equal to inner product of T alpha j and alpha k. Also, if matrix representation of T star with respect to order basis B is equal to say capital B, then AJK equal to BKJ bar. Let me quickly solve this problem, please. Given B equal to alpha 1 to alpha n and orthogonal order basis for V. So, this implies for any element alpha belongs to V, alpha can be written as sigma inner product of alpha alpha j and alpha j. This is already we have seen j equal to 1 to n. So, this relation is already known to us. You can of course quickly check that suppose alpha is equal to sigma C I alpha I, taking the concept that alpha 1 alpha 2 an orthogonal basis, if you take inner product then we get the what to be the corresponding C I. So, anyhow, so we can immediately find out the alpha can be written like this. Given is the matrix representations of the operator T. So, this implies, so T of alpha j can be written as sigma A k j alpha k, k equal to 1 to n. So, this is my second equations and first equation is like this. So, again one can write down T of alpha j also following star, this will be equal to sigma inner product of T of alpha j and alpha k k equal to 1 to n. So, if you compare double star and triple star, so this implies that Akj equal to inner product of T alpha j and alpha k. Again, if given matrix representation of T star with respect to same order basis equal to say this B matrix. So, this implies T star of alpha j will be again equal to sigma T star alpha j and alpha k and alpha k. So, this will again show that your Bkj will be equal to inner product of T alpha j star and alpha k. But this is equal to, one can write down alpha k and T star alpha j from the property of the inner product. This is equal to, I can write down from the definition of adjoint operator, this will be equal to inner product of T alpha k and alpha j bar. So, this is equal to A j k bar. So, B k j equal to A j k bar. So, this is the relation between the matrix representation of the operator T and T star with respect to given orthogonal basis. We will discuss more about this with more examples in our next class.